What is the acid strength from strongest to weakest? Okay, so this question was about, well, comparing pKa's of compounds based on their structure. So there's a few different factors that you should have learned in the class, things that affect the acidity of a compound. So generally, there's electronegativity. Oops, electronegativity is one. The size, the electronegativity of the atom bonded to the proton to be lost. The size of that same atom. Let me think. There's the hybridization, so more S character, more acidic, right? So an alkyne is more acidic than an alkane, right? So let me think what else besides. So electron delocalization, right? Resonance. That will stabilize the conjugate base, increasing the acidity. And for this problem specifically, we care about inductive electron withdrawal. And so it's about how the substituents of an acid can affect the pKa based on substituents that are attached to the acidic functional group without resonance, right? So there's no resonance in this compound, but for example, this is let's write this as this is a carbon with 3 fluorines on it, and fluorine is really electronegative. So the electron density of this molecule goes over this way, right? And that makes this proton easier to pop off, makes it a stronger acid. Now, the closer this substituent is to the functional group, right? This is the carboxylic acid functional group, right? So the closer this is to the functional group, to the central carbon there, the more acidic it will be. So basically this CF3 is closer than this CF3. So 3 will be greater than 2, right? And so this guy also, this is CCl3, right? So this is carbon with 3 chlorines. Carbon, chlorine, chlorine, chlorine. And chlorine is less electronegative than fluoride, right? Periodic table, right? Imagine a big box. Electronegativity increases as an arrow pointing to the top right corner. So F is as electronegative as it gets. Chlorine is just below F in the periodic table, so it's a little less electronegative. So CF3 is going to beat CCl3, but this guy will beat this guy because the inductive electron withdrawal group is further away from the acidic proton. Okay? And then this guy, there is no inductive electron withdrawal in this guy because these are relatively nonpolar bonds. So there's no, the electron density of this compound is just towards the O, right? Yeah. So what it does, what the inductive electron withdrawal does is, right, if we have like a carboxylic acid, RCOH, right, and we donate that proton, RCO minus, right, so now there's a full minus charge on this oxygen. If we put electronegative group, just En for electronegative down there, right, now that's going to pull away some of the minus charge so the O doesn't have to bear all of it. Although O is electronegative and good at bearing negative charge, right, we can remove some of that and make the conjugate base a little more stable. make the acid stronger, right? So that's what's happening here. And so this has the most electron density over here to help this O minus handle some of the electron density after it donates a proton. So 3 will be the top, so we should have 3 first, and 3 will be greater than 4, which is greater than 2, which is greater than 1. So C is our answer.